You know the exact feeling. You've just spent 40 hours straight in your CAD software meticulously modeling this incredible new assembly. Every single tolerance looks pristine on your monitor. Every mate is perfectly constrained. So, you send it to the machine, hit start, walk away to grab a quick coffee, and 30 minutes later, you pull out a shattered, warped, burning mess of a part. Literally a completely useless physical piece of trash. It's a heartbreaking rite of passage, really. So, my fellow engineers and designers, how exactly do you avoid making expensive scrap? Well, welcome to the club. Today, we're going to talk about the massive reality check that every digital designer eventually faces when they step off the computer and walk onto the fabrication floor.
Welcome to this explainer on subtractive manufacturing and fabrication. It's genuinely amazing how CAD software will happily let us draw, well, pretty much anything. You want floating parts? Sure. Mathematically impossible sharp inside corners? No problem. Walls with zero thickness? Go for it. But out here, the laws of physics are what actually dictate what you can build. Subtractive manufacturing is fundamentally about removing material from a raw block or sheet with absolute, unforgiving precision. But to do that without entirely destroying your part, snapping your incredibly expensive tools, or, totally crushing your engineering ego, you have to truly understand the physical constraints of the machines you're commanding. We've got to learn how to translate digital perfection into physical reality.
Okay, let's dive into this. Here is our technical blueprint for the next few minutes. We'll be looking at design for laser cutting, then CNC milling and CAM workflows, and finally, laboratory safety.
Starting off with Section 1, Design for Laser Cutting, focusing on vector graphics and kerf. Let's start with the precise, mathematically driven 2D world of laser cutting. A laser cutter is essentially just a super high-powered beam of light that vaporizes a 2D path right through a sheet of material, usually wood, acrylic, or cardboard. It's incredibly fast, but a heavy mechanical gantry flying around at those high speeds needs a very specific type of digital instruction so it can accelerate and decelerate smoothly. If you're used to working with JPEGs or PNGs, well, those are raster graphics. They're just static grids of colored pixels, and a laser cutter doesn't have a clue what to do with a pixel. Instead, it needs vector graphics. These are built entirely on mathematical equations that define exact lines, curves, and polygons. This is absolutely essential because vector paths can scale infinitely without losing a drop of quality. They give the physical laserhead an exact continuous coordinate path to follow, which ensures absolute geometric accuracy. But here is exactly where the digital world violently collides with physics. When you draw a line in CAD, that line has absolutely zero physical thickness. It's just a theoretical boundary. But a laser beam, that's a physical entity. It has a real diameter. As it cuts along your perfectly mathematical line, the intense, highly focused heat causes a rapid phase change. The solid material directly under the beam doesn't just quietly disappear. It instantaneously vaporizes into a gas. This means the laser literally leaves a physical gap in your part. In manufacturing, we call the exact width of this vaporized, removed material the kerf. Now, what's really interesting is the sheer scale of this number. A typical laser kerf is between 0.002 and 0.005 of an inch. To a novice walking into the shop for the first time, that decimal seems microscopic. It's so tiny that it's incredibly tempting to just ignore it entirely and assume the machine will just sort it out. But let me tell you, from bitter, frustrating experience, you cannot negotiate with physics. If you ignore a 0.005 of an inch gap on a precision part, that tiny width of a laser beam will completely ruin the interlocking joints or press fits of your final assembly.
Think about the actual difference in outcome here. If you attempt a direct, uncompensated line-to-line fit right out of your CAD software, material gets vaporized equally on both sides of your mating parts. The result? A wobbly, rattling failure that literally just falls apart in your hands. But if you apply proper engineering principles to create a kerf-compensated fit, you change the entire game. By intentionally offsetting your digital cut paths by exactly half the kerf width, you account for that vaporized material, so when those final physical parts come off the machine, they will press together with a beautiful, structurally sound, incredibly satisfying friction fit. But hey, kerf isn't just some annoying gap you have to compensate for. Clever engineers actually take advantage of it to create absolute magic. By cutting highly specific, repeating geometric patterns into a rigid sheet of wood or plastic, you vaporize just enough material to weaken the structure in a highly controlled way. The super thin webs of material left behind can actually undergo tension and torsion safely. This miraculously transforms brittle, rigid materials into flexible, compliant mechanisms. We call these living hinges. Whether you're making a flat hinge, a complex butterfly hinge, or sweeping curve bends for an enclosure, you're literally utilizing the fundamental physics of subtractive manufacturing to generate entirely new material properties.
Moving right along to Section 2, CNC milling and CAM workflows, the 3D subtractive system.
Let's see how this builds into the incredibly robust, multi-axis world of CNC milling. If laser cutting is all about vaporizing a 2D path, CNC milling is about forcefully carving out a 3D block using aggressively spinning metal cutting tools. To bridge the gap between your 3D CAD model and the heavy physical machine, we cross over using the CAM workflow, that's computer-aided manufacturing. This is a sequential process that translates your geometry into machine-readable commands. Step 1 is the stock setup. You absolutely must tell the software the exact dimensions of your raw material. If you're off by even a fraction of an inch here, the machine might plunge a spinning tool straight into solid metal when it's expecting empty air. Step 2 is toolpath generation, where you define exactly how the cutter will move. And step 3 is the G-code export, which generates the raw line-by-line coordinate language that the CNC machine will actually execute.
During that toolpath generation phase, you're going to rely on a few foundational operations. First up is facing. You see, raw, unmachined stock is almost never perfectly flat. So a facing toolpath simply shaves off the entire top layer to establish a perfectly flat, mathematically true starting plane. From there, you typically move on to adaptive clearing. And actually, this is a brilliant algorithmic dance. The software calculates a highly optimized roughing path that removes the bulk of the unwanted material, but it does so while maintaining a strictly consistent load on the cutting tool. By ensuring that the tool is engaged by exactly the same amount constantly, it prevents those sudden, terrifying spikes in force that could instantly snap your cutting bit.
Setting up these toolpaths isn't just about drawing lines on a screen. It is fundamentally about the math and physics of cutting metal. And that all comes down to balancing speeds and feeds. Speed is how fast the spindle rotates the tool, measured in RPM. Feed is the linear movement, basically how fast the tool is being forcefully pushed through the material, measured in inches per minute. Failing to properly balance these two variables for your specific material leads to absolute disaster. If you feed too slowly in a soft material like aluminum, the friction builds immense heat. The aluminum literally melts, friction welds itself right into the flutes of your cutter and snaps the tool. If you feed too fast in a hard material like steel, the mechanical force just shatters the carbide instantly. Catastrophic tool failure is loud, it's expensive, and it's completely avoidable if you just do the math.
And that brings us to Section 3, Laboratory Safety, Surviving the Shop.
This is a massive, critical shift in tone. We are shifting gears entirely from how to build to how to survive. The fabrication lab is an incredible place, for sure, but it is filled with industrial machines that possess relentless torque you absolutely cannot fight and lasers that will instantly blind you. So these are the mandatory physical requirements to mitigate that risk. Safety glasses are required at all times. Flying razor-sharp metal chips do not politely give you a warning before hitting your eye. Steel-toed books protect you against dropped heavy stock. You must tie back long hair and remove any loose clothing, dangling sleeves, or jewelry. Let me be incredibly clear about this. A 3-horsepower CNC spindle does not stall out like your battery-powered hand drill at home. It possesses massive industrial horsepower. If a hoodie string gets caught, the machine will not stop. It will pull you right in without a single drop in RPM. And before you ever hit that start button, you need to physically locate the bright red emergency stop button. So the absolutely crucial point here is this. You must abide by the industry standard 2-person rule. You must never, ever work alone in a fabrication lab. Even the most seasoned veteran machinists working late-night shifts strictly abide by this. If you have an accident, if you get entangled, or if a machine catches fire, you desperately need someone else there to hit that emergency stop and call for help. A shop without supervision is a shop you simply do not walk into. Period.
Now, let's do a quick quiz about making terrible, life-altering workshop decisions. Polyvinyl chloride, or PVC, is a super common, incredibly cheap plastic. You might be extremely tempted to just throw a sheet of it into the laser cutter to quickly prototype a part. So, why must you absolutely, under no circumstances, ever do this?
Well, because part of fabrication is kind of being a minor chemist. When you vaporize PVC with the intense heat of a laser, the thermal breakdown of that plastic creates highly toxic chlorine gas. Yes, the exact same gas used historically as a deadly chemical weapon. This gas will rapidly corrode and destroy the expensive linear rails, optics, and electronics inside the laser cutter. But much, much worse, it will violently ruin your respiratory system. Material Safety Data Sheets, or SDS, exist for a very good reason. You must know exactly what chemical compounds you are vaporizing before you ever fire that laser.
Which brings us perfectly back around to the core question of our journey today.
You see, a beautiful CAD model sitting perfectly on a glowing screen is ultimately just a hypothesis. It's merely a digital idea. But to pull it into physical reality, you have to successfully navigate vector mathematics, the physical kerf of a vaporizing beam, the precise thermodynamics of spinning end mills, and the unforgiving, mandatory safety protocols of the shop floor. So the next time you boot up your software and start sketching, ask yourself, are you just designing for the screen, or are you actually designing for the real world? Thanks for joining me on this explainer, and I'll see you in the lab.